So, welcome at the seminar of our dear friend Laure Petrucci from Paris. It's not her first seminar here, and as the previous one were very nice, this will be even nicer despite the weather.
Well, thank you. We should see.
I'm sure I will bet on it. Please.
Yeah, so that was, I would say, a short time request from the other.
Yes.
And so, I've, since I did many presentations here, I chose last one that was some common work with Jaco van der Poel. And Jaco, who was at the University of Twente, presented this a paper, a joint paper at Forte last year, in June, about parameter synthesis algorithms for parametric interval Markov chains. So it's a bit different from what I've shown you. So it's slide, it's the naming iterate. But anyway, and it's now no more in Twente, but in Aarhus in Denmark. So I will start by talking a bit about the model, parametric interval Markov chain. So giving some motivation and showing what are the contributions of this work before getting into details. The main property that we are interested in is consistency for parametric interval Markov chain, and I will define inductive consistency and co-inductive inconsistency for these models, and we'll give new upper bounds on this n for n consistency. I will then present some algorithms to put that into practice, and these algorithms are consistency checking for interval Markov chains and parameter synthesis for parametric interval Markov chains. So these two models, in fact, are very similar. They only differ by the fact that PIMCs have parameters, whereas IMCs do not. Then we do consistency, so we check this property for IMCs, and for PIMCs what we want to do is to synthesize some parameter values for which the model is consistent or some state is consistent. That is to obtain some formula saying for parameters that satisfy these formulas, then the result is correct. And I will give you some experimental results. So it's preliminary experimental results, since it's some scalable examples, but not real-world examples. Okay, so let us first recall what Markov chain is and how we will present it and how it works. So basically it looks like an automaton where you have some locations or states, and you can go from one location to another with some probability. So the sum of outgoing probabilities for each node should be 1. So if you look at node 0, the outgoing arcs are labeled with 0.7 and 0.3, that adds up to 1. And from 1 to 3, it's 0.5. You have a self-loop on 1, which is also 0.5. So that means that from from state 1, you have a probability of 1/2 to stay in 1, and a probability of 1/2 to go to 3. And some transitions might have a 0 probability, such as this one, and here it's dashed. And you will see why afterwards we use this. Okay? So that means that from 2 to 4 you cannot go from 2 to 4, and you explicitly say that the probability is 0. So there are a certain level of, you have levels of uncertainty in Markov chains because you use probabilities to quantify this uncertainty, and that allows for modeling different kinds of systems, so sampling failures, user behavior, which are due to the environment, so who interacts with the model, with the system. Or you can have problems of systems biology, where the choices are driven by nature things. And you can have also probabilistic algorithms and protocols that have some probabilities embedded in the design. But in practice, the exact probabilities are generally not known. So you don't know whether it's exactly one path or it is roughly one path. So therefore, a possibility is to replace these probabilities with intervals or parameters, or intervals with parametric bounds, as in parametric interval Markov chain. So instead of saying, well, I know that to go from that state to that other state, the probability is one half, you would say, well, I know that to go from that state to that other state, the probability is in between two bounds, within an interval. Okay. So when we explore the possibilities and we do exhaustive analysis of the model, we want to synthesize constraints on parameters in the case of parametric models, and that allows for adding something quite general, robust, to have correctness constraints on bounds, and to allow for dimension. So let's have a look at different models derived from Markov chains. So the first one, PMC, which is known in the literature as parametric Markov chains, only has parameters, no intervals. And it's in particular implemented in some tools like Prism in Oxford. So here you have the same constraint as before. You have the outgoing arcs that add up to 1. But here you know that from 0 to 1 you have a probability p to take this arc. And therefore you have a probability 1 minus p for the other arc. Right? But you don't know what p is, and synthesizing the value of p is one of the issues there. You also have interval Markov chains that have intervals but no parameters. So here you have a probability to go from 2 to 3, that is between 0 and 1/4, and a probability from 2 to 4 that is between 1/4 and 1. So yeah, you in fact the only solution would be to have 1/4 on the left side and 3/4 on the
right.
well, no, it's not the only solution. You can have 0 and 1 and up to yeah. So that is exactly what the problem of consistency is.
Yeah, sure.
So if you choose something within this interval, then what you choose in the other interval must add up with it to 1. And you can see that here it's possible, and there are several possibilities to do so. In PIMC, so we have parametric intervals. These parametric intervals, well, they look like interval, like this. So you have a lower bound and an upper bound. And they can be point intervals like this. I have a probability between P and P, so it's P. Or they can be some normal intervals with a bound that may be a parameter. So here you have between 0 and R. R being a parameter, you don't know what it is yet. Right. These parameters, P, Q, R, they are the same for any place where they occur in the model. That is, this P is the same as this one, but it's also the same as this one. So once you choose a value for P, then in the whole model it's the same value. Okay, so you can see already that it's a bit more complex because you have different possibilities that are locally possible, but maybe not globally possible. So an IMC, the interval Markov chain, is formally written as a triple, where you have the states, the initial states as 0, so in our example it would be the root state, well here 0, here actually it's 2, but 0 here. And a function that associates with two states an interval. So this function phi associates an interval with every pair of states. So from 2 to 3, it would be this interval 0, 1/4. And it's denoted by phi L and phi U for lower and upper bounds of the interval. And PIMCs generalize both PMCs and IMCs as they handle both intervals and parameters. The formalisms of these formalisms, all these, can be viewed as specifications of for Markov chains. If we make a choice for a parameter, or if we make a choice for a value within an interval, then we can replace the values and obtain a Markov chain. So they would describe a set of Markov chains. The consistency property states that the specification admits at least one Markov chain, and that can be defined as a simulation. So why consistency is not that easy? The synthesis problem in parametric interval Markov chain consists in saying for which parameters is the result IMC consistent. So if I have this example, what happens? Here I have two outgoing arcs from 0 that are with the interval 0, 1. So I can pick one value in one and then find the corresponding value in the other one. So if I choose 0.5 in one of the intervals, then I will have, for consistency, to choose 0.5 in the other one. Then when I have parameters on arcs, it's a bit more tricky. If we do the synthesis for this model, we obtain this result, saying that Q, it's interesting because you don't have P in here. So what about the value of P? You should have Q between 0.3 and 0.7, or Q equal to 1. And that is the result for it to be consistent. Okay. So, what we note here is that state 4 is not consistent. Oops, going too fast. State 4 is not consistent. Indeed, from here, for this interval to be correct, we need P to be less than 0.3, because the lower bound must be smaller than the upper bound. And here, for this interval to be correct, we need P greater than 0.5.
Doesn't that?
Exactly. So it's not possible. It can't be both smaller than 0.3 and bigger than 0.5. Therefore, this state 4 is inconsistent. Okay, so can we get rid of it? The answer is yes, because here we have an interval that says between 0 and 0.5. So we can choose 0. And therefore we will never get to 4. And 4 is useless. It's just represented in the picture. And that's the reason why we have this dashed arc here now. Okay, so we have, in this solution that we found, we have two possibilities. One would be to go from 0 to 1 and avoiding to go from 0 to state 2. And in this case we find that Q plus 0.3 must be smaller than 1, and the reason is here that Q plus 0.3 is the lower bound, so it should be smaller than 1. And also that Q must be greater than 0.3 for this interval to be correct. And Q plus 1 greater than 1 is obvious. Okay, the other possibility, so that leads to this first part, and the other possibility is to try to go from 0 to 2 and avoid going to 1. And in this case, what happens? I go from 0 to 2, and then I have this arc, which says 0q only, and so you must necessarily have 1 there. So q is 1. Okay, so the contributions in this work were first on the theory of consistency, where we had new definitions that are both inductive as the one that was existing before, but which has been simplified, and the other one that is new, which is co-inductive. And we have, well, the full proofs were done and checked in the theorem prover PDS, so they were automatically checked, and that is, well, that is nice. Then we derived some algorithms for checking the consistency for interval Markov chain with a backward algorithm that is co-inductive and a forward algorithm that is inductive. All this was implemented in Prolog, so it's really a prototype tool, with the constraint solver that is provided with the Prolog environment. So we didn't have to implement a constraint solver, it was already done within the language, the environment. We also have implemented algorithms for parameter synthesis for PIMC consistency, both backward and forward, so as the previous ones. And they were implemented using also the PAMA polyhedra library, which works on polyhedra and convexes, and that allows for deriving constraints on parameters quite easily. Okay, so let's just look at the consistency. For an interval Markov chain, so we'll do most of the things for interval Markov chains and then speak about parametric interval Markov chains. So let us look at the consistency for a state S, that is the state of interest. So is this state consistent? And in defining the consistency, we'll look at it considering a set X of candidate successors. We have seen in the example before that state 4 was not possible as a successor of state 2. So basically here it will help to say, well, from state 2 I can go to my successors but not 4, because it won't be in this set X. So the first part is local consistency with some probabilities, probability intervals, lower probability, upper probability. So in the local consistency we have several parts. First, the sum of upper bounds should be correct, greater than 1. So it's this property up of Sx. So if I add up all the probabilities that are outgoing state S and that go to a state that is in my candidate successors, then I should have more than 1. So the upper bounds add up to something that is more than 1. Similarly, for the lower bounds, the lower bounds, they should add up to something that is less than 1. And finally, I have some local part, which states that if I go from S to an element of X, then I have the lower bound that is smaller than the upper bound. And if I have a state which is not in X, then the lower bound must be 0, because I must be able not to go to there. So to go there with probability 0. Right? Okay. And this is monotonic. When we look at global consistency, what happens? So we have this monotonic function of local consistency, And here we are looking at an interval Markov chain. So there was a definition of consistency and consistency that was inductive, and that was given by Delahaye, Lim, and myself. That was stating that at level, so it was inductive in the sense that you look at some level and then you look at the next level of consistency and so on until you reach a fixed point. So initially, the consistency at level 0 is everybody is consistent, okay? And then the local consistency is checked at each level. So local consistency is checked on level on the consistent states at level n, and gives the set of consistent states at level n plus 1. So the intuition is that you can do n locally consistent steps. Okay? So you can take n arcs and keep being consistent. So that was expressed in such a way. There exists a set X such that the local consistency from S to these successors in set state X is satisfied, and for all elements in X, the consistency at level n is satisfied. We have rephrased it into this new definition. So there is, we look at the union on the set X that are possible outputs from S, so in the support of S, such that the local consistency is satisfied and X is a subset of cos A. This is completely equivalent. The co-inductive consistency, which was a new thing in this work, is based on looking at the greatest fixed point of this local consistency. So there is no more this n level that you repeat. And consistent states, in fact, intuitively, they keep doing consistent local states. So each time they remain consistent, and they remain consistent until the end.
What is this? Its greatest fixed point?
Pardon?
What is this greatest fixed point?
So, well, if you repeat,
yes,
you have a stable state.
What is the greatest?
Well, it's the usual greatest fixed point procedure that is used, and
you need to theoretic conclusion.
Okay, it's a sense of.
Yeah, okay, conclusion.
Yes, when it's state
Sure.
space, so it's a transport from state space to state space, and the fixed point is a subset of the set of state space for the greatest point.
Yeah.
It would be good why to explain why it is the greatest one, not the least one.
When it's the greatest one. Because if it's not the greatest one, then there could be something that becomes not consistent. Well, I have to check the details again.
It makes sense, it should be the greatest.
Yes.
In my opinion, I just...
Yeah, but I have to check the details
Yes,
to
yes.
exactly
Yeah.
answer the question. So what we have shown is that the initial state is consistent if and only if there exists a Markov chain that satisfies the interval Markov chain specification. So if you can pick some probabilities in the interval and have a consistent Markov chain. We have shown also the equivalence of inductive and co-inductive definitions, and that is assuming that phi has a finite support. then if the state S is consistent, well, state S is consistent if and only if for all n it's in constant. So it's equivalent to say that it's consistent and that at all levels of inconsistency it's correct. So the inductive and co-inductive definitions agree.
Does this mean, excuse me, does this mean that the least fixed point and the greatest fixed point are the same?
I'm really not sure what the least fixed point would mean in case of consistency.
It seems that the union of cons sub n is a kind of least fixed point.
Is a kind of what fixed point?
Least fixed point.
Yes.
Maybe.
Maybe.
It might be so, yes.
Yeah, well,
Well, it's,
I think it relates to the other question. And,
yes, absolutely.
So, yeah,
It
well,
requires-
I'll check the details and let you know. For infinitely branching IMCs, so if we don't have this finite support, that is not true. And in particular, if we take this example where we have an infinite number of states, t0, t1, etc., and a state t here, and we go from t to any of these with a probability 0, 1, and then we can go up the chain to t0, well, down the chain to t0, then you can see that t is not consistent in the sense of cons, but for all n, t is in cons n. And so that is that shows that this finite support is important, which is not really an issue because in real life it would be finite.
Why it is not in cons?
Why it is not in cons? It is because so here you would like to have a greatest fixed point on the local consistency, and if you have something infinite, then you cannot achieve this greatest fixed point. Because you always add constraints and you never stabilize.
So why not the set of all states is not a fixed point? The set of all states.
The set of all states? Yeah, because here you have an infinite number of states. So it doesn't work. If you take them individually, you can
If I assume all of them are consistent, then I'll see of them.
Yeah, but you have to prove that all of them are consistent. And that doesn't end. So in practice, we have anyway finite models, so it's fine. The question is that if we apply this inconsistency thing, if we apply this inconsistency computation, the question is for which end do we need to check the consistency? So if we want to check that the model is consistent, then how many steps do we have to do with checking the inconsistency? So originally in the paper by Verheyen and myself, there was an obvious result that was saying we have to look at the size of states, because you look always at the successors, so you can do it as many times as there are possible successors, or if you have a chain. Of course, for a finite interval Markov chain. Then, well, we can refine this by saying that if we take the length of the longest simple path, then it's sufficient to take this length as a bound. The problem being that the computing this bound P is NP complete. So, well, we could say it doesn't help. This bound is smaller than or equal to S, so it should be nice because we would have to do the procedure less times. But so we have this disadvantage, but however it can be computed for trees. So, well, in this case it's fine. Or over approximated using strongly connected components, so it helps as well. So we can, even though we can't compute it precisely, we can have some better bound than the number of states. The other definition of consistency, the co-inductive one, doesn't need this n at all, because we compute we do the computation until the fixed point is reached. So, what are the associated algorithms? So let us first look at the co-inductive or backward algorithms. Initially, we start saying that all states have consistency true, and we assume that they are all consistent, and we use a working list Q that is equal to the set of states to be eczema. Then we'll repeat a loop for all states that are in Q, so we take one in Q, and we will remove from the consistency set all the local counterexamples. So if we have picked R from Q, we'll look at its successors and check whether its successors are consistent or not. If the successor T is not consistent, if it's consistent, it will go to this set X, and we can check the local consistency of R with respect to X. So we look at those that are just one step further, see whether they are, for the moment, consistent. If it is the case, if we have the local consistency with these, then we are rather happy. If they are not consistent, then we know that we are not consistent. So in this case, we can say we found a successor that is not consistent, and therefore for which the local consistency is not satisfied, and therefore we can already say that it's false. And for all predecessors of R, we will see if the predecessor was consistent. Then we have to recheck it again. So I have moved from R that was consistent, it became non-consistent, then I have to tell the predecessors of R that something changed, and you have to check again whether it's possible. The forward algorithm is doing M consistency checks. So here you have the consistency for a level M from a state S. And we are doing consistency checks with respect to M-1 successors. So the procedure is applied at some level M-1, and we apply it again to level N. So here we would have a set of states that are successors of our state S of interest, and that are consistent at level n-1. So it's all my consistent successes. And if the local consistency with respect to the set C is satisfied, I'll be happy. Otherwise, I can conclude that I'm not consistent. And we use two things. So there is this optimization where we have some caching, this PC and NC, so it's positive and negative results that are recorded. And so we would say that these positive results, saying, okay, I know that for some level, the consistency is proved, and the negative results would say that at some level, the non-consistency has been obtained. And that allows for having faster checks, because if we know that at some level that was smaller, we had a negative result, then we know that the result is necessarily negative and we don't have to check it again. And similarly, if we have already obtained at a higher level that the consistency was satisfied, then we know that it must be satisfied at a lower level. So that allows for avoiding some recursion in here, because sometimes you would take a branch, find some results, and then, well, backtrack and take another branch and ask for the same level of consistency for the same node. Okay? So therefore, we would say, okay, I already know the results, I don't have to compute everything all over again. In the case of PRMCs, we have done a synthesis with an inductive algorithms, and for a fixed set X, the local consistency of X is a constraint on the parameters of the PIMC that we express in the form of a convex polyhedron. And so here we have, say, two variables, V0s and Vn+1s, where the first, the second thing is a state, and the first one is a level of consistency that can be repeated. And this leads us to some synthesis algorithm here, where we have a basic data structure that is obtained by using PPL, where we use the true and, well, the true and empty operators, the intersection between polyhedron and the unit. Here in this, the problem that is in this algorithm is here. We do a union on all possible sets X that are in the subsets of the supporter phase. Because to synthesize parameters, we must look at all possible sets of successes. So I can take, it was in the very first example, there was something where I was looking at state from 0 to 1, and then at state from 0, at transition from 0 to 2. And there are two possibilities, two possible X's, and I have to look at all cases, right? So I have to examine all subsets of the supporter base. And that leads to an exponential program. But in this, in the implementation of this algorithm, PPL does automatic constraint simplification, so we don't have to care for that. And there's some caching of results that is achieved. In the co-inductive algorithms, it boils down to solving a recursive equation system of a set of polyhedra. And, well, this is a greatest fixed point computation starting from the set of all possibilities for true. Okay. Yeah. So it's similar. We have the solution initially it's true, and when we repeat this procedure if the solution is included in the solution we have already found, then we can say that the solution is the new we found one, and we repeat it again. So as previously, we use a set of states that has to be labeled until this ends. So that has to be checked, and if the solution is decreasing, then the predecessors must be rechecked for the same reasons as previously, because you said, well, it's no more in the solution, and therefore the result might be wrong. So this equation system can be expressed with some variables, so one per state. So here is an example. So it's still the same example as before, and you can define the variable per state. So Vs for state S. So V0 here, it would be, well, either I go to to 1 only, so that would be V0 is the same as V1, or I go to 2, so V0 is the same as V2, or I go to 1 and 2, so it would be the same as V1 and V2, which must be satisfied. And you do the same for all states. So here, if you are in state 1, you can see that the possibilities is either going only to state 1 again, so this is V1 equals V1, and I can go to well, this has been reduced a bit. So it's V1 and V3, and these things on the parameters, because Q must be greater than 0.3 and less than 0.7 for the upper bound to be correct, etc. So you can express all variables like this, and then you can solve the equation system by repeating some resolution. So initially all things are true, and then at the first step, what will happen? V0 equals V1 or V2, both are true, so it remains true. V1 was equal to V1 and 0.3 smaller than Q smaller than 0.7. So V1, the previous one, was true, so there's only this equation left. And in V2, if we check this, we obtain this P plus Q greater than or equal to 1, because the rest is eliminated. And V3 equals V3 remains true, and V4 equals false. The result is false. And we continue again. So second iteration, I take the equations and I replace with the values that are obtained at the first iteration. I obtain these results, and at the third iteration we get the final result, that is this one. And you can see that here is what we had at the very beginning on this example. And in fact, if we want to repeat it, well, it's exactly the same. Nothing changes anymore. Okay, so that was another way to implement. So we did some experiments, and to do that, to have something scalable, or at least a bit scalable, and play with the algorithms, we use the... What?
What set is it? Those dining philosophers.
So the dining philosophers are a classical toy example, where there are philosophers around the table, and they have chopsticks, and they want to eat pasta, and they share their chopsticks. So we took the model that is in the PRISM toolset. So PRISM is probabilistic is for probabilistic model checking. So it's a tool that is quite well known and developed in Oxford. And so we took their implementation of these dining philosophers, and especially because they have probabilities already on this model, and we replaced, but they have fixed probabilities, so we had to replace them to include some parameters and to include some intervals. So we looked at, we picked some probabilities and replaced them by what is here on the left-hand side. So here we had one parameter only, and we replace some probabilities with the intervals p plus 0.1. All those probabilities, all the other probabilities, they are fixed, and so it's the interval, the probability in itself. We have looked at the probability intervals ranging from 0 to p and from p to 1, and having two parameters from p to q, or from 0 to p and 0.3 to q, and from p to 1 and 0.3 to q. So different values to examine what was going on in different settings with one parameters, two parameters, with bounds that have both have the parameter but which are not a single point, or ranging from 0 to parameters 1. Right. The models were for 3 philosophers and 4 philosophers, and it's already quite big. We used the different algorithms. So both the inductive n-inductive one and the n-inductive, including the optimizations, the one with the NC and PC things that were cutting out branches, and the co-inductive algorithm that uses the PPL library, in which we don't have to specify this number n, because it's the fixed point thing. The results are the following. So without optimization, we can look at n consistency for n equals 2 or n equals 3, whereas with optimization we can go to n equals 10 or even n equals 50. There is a timeout that was set to 1 hour in these experiments, and you can see that there are quite a few timeouts in the first case for n equals 3, and in the second case for n equals 50. So the optimization is quite efficient in the sense that we get more results and less timeouts. There is some extra, there is some, it's not overrated. These ends are different, so we go much further there. With the PPL library and the co-inductive algorithms, we didn't have any timeouts on these examples. So then the computation was done for any n. Well, n is not specified. So that is the actual result, which is quite nice and shows it's efficient to use. So to conclude, we have shown a co-inductive definition of consistency, which is simpler in the sense that there is no n, we have this infinite support that we can take care of. Well, it works with the infinite support, whereas with n, you can't have something with an infinite support. Then the inductive definition, was bounded by the longest simple path instead of the whole set of states, and the algorithms have shown some optimizations for inductive and consistency that are effective, so caching and some assumption. And for the co-inductive algorithms, we have better results. So it's superior as we don't have to care for this n, and it works for all s, which is not the case for this n consistency, where you have to say for which state you're looking for the result. Possible extensions would be to have an efficient implementation, because this was really a prototype and quickly implemented in product, with more experiments and more parameters, and more sensible case studies. And we would like to try to find something to avoid this enumeration of all possible successive subsets. So some heuristics to reduce the set of possibilities and checklist. Thank you.
Thank you, Laura. Well, we have asked quite some questions during the presentation, but I invite more questions. Certainly the subject was interesting.
I have a question. What did you use Prism for?
Prism, we just took the examples.
That's it. Are there any methods for parameter synthesis in Prism?
Yes, but it's not the same type of models that they are using.
Okay. Okay, and one more question. Are there any other methods you could compare your experimental results to?
For the same kind of models?
Well, or similar.
For the same kind of models, the answer is no.
Okay.
For similar models, well, we could compare to parametric time automata, but I think some of the techniques in the exploration are a bit similar, but the constraints are different. So what you compute is really not the same thing. But the ideas of doing backward checks or forward checks are also used in parametric time automata.
More questions? Michał?
I have a question.
And Jan.
I had some problems with understanding the fixed point algorithm with those consistency constraints. That means that when you're computing consistency from local consistencies, are you doing a kind of global model checking, or do you keep remembering the initial state of the part?
You don't need the initial state. You do it for all states. So in fact, for all states, you compute the new values, and if in some of your successes something changed, you have to be recomputed. So it doesn't depend on the initial state.
So backtracking is crucial.
So the initial state is not used at any.
No.
Okay, so you mentioned the convex polyhedra, so it means that does it work only for linear constraints, or you can have constraints like p squared plus q squared?
No, it's linear constraints.
Any more questions?
Which is basically makes sense because we compared to sums of parameters compared to some values. So in the model we have parameters and etc. Or it can be p plus q or linear combinations of parameters. But
no need for other constraints arises.
No.
You are using probabilities here, the interval probabilities. What about other methods of representing uncertainty? For example, fuzziness, lift models, and so on, which are by definition intervals.
Yeah. Well, we didn't look at that yet. It was already complex enough. There are quite a few works on different kinds of stochastic automata or probabilistic automata that, some different kinds of Markov chains that look at these methods, fuzzy methods and things like that. But we didn't investigate that. And yeah. there is quite some literature on this. But it's not the same kind of model, so they wouldn't use parameters and intervals, and in general, they wouldn't have parameters. Well, for those that are certain.
Other method of checking whether this works or does not work is simply to choose uniform random variables from those intervals and check whether you can simply whether it will work or not. Yes?
Yeah. Yeah, but then you don't have all the possibilities.
Yes, probably.
This is also always a trade-off between having a set of solutions and having a set of alternatives, which is that's true. So, well, I must say that these things on consistency in parametric interval Markov chain has been applied recently by Benoît Delay to a real problem of drone. You saw the presentation at Syncope, didn't you? To security of drones' flight plans, so that drones wouldn't crash on the ground. It's under some surveillance operation.
Just a comment, to have a solution, you can just encode everything as a formula, give it to a SMT solver, and then you will get a solution if it exists.
A solution.
Yeah. Yeah.
And that's the way to solve that problem.
Yeah.
Well, any more questions? So let us thank Laure again.